Students, so we're continuing with the section we are doing on digital electronics, on Boolean algebra, on binary variables. So in the last video I've sent to you, we've covered the section on universal gates and manipulating with Boolean expressions using De Morgan's law and other Boolean rules, like we've seen here, for example, these rules here, which you should familiarize yourself with. Now, today we're going to look at topics related to problem formulation. So the first topic we're going to look at is problem formulation analysis. So by using a Boolean variables, which can be true or false, you can very well represent possible combinations of input factors which are going to produce an output. So you can see here some notes are given, but I'm going to just straight away go to one example. There are 3 examples given in your handout. So the first example here of persons X, Y, and Z having different behaviors depending on different conditions like temperature, music, being oriental or not, and whether there's crowd or not. So this is one example you could try on your own. The example which I'll be using to illustrate what is problem formulation analysis is here. Okay, so let's look at that together. The result of a series of mathematical operations on a given starting number produces the final result. The sequence of operation can be, so here are our inputs. So you have a starting number, it can be any number, and then you start carrying out certain series of mathematical operations like multiplication by 5 is the first one, as shown here. Then you could divide by 4 or not. And finally, the third step is adding 7. These are the possible operations, and the sequence should be followed in this particular order. So you can't, for example, divide by 4 first and then multiply by 5. So it should be in this order. Though one or more steps may be skipped. For example, if the first step is skipped, it means if you use a Boolean variable, let's just say you call it A, to represent whether you multiply by 5 or not. So when A takes a value of 0 means you did not multiply by 5, and when A takes a value of 1 means true, you multiply by 5. So by using different Boolean variables to represent multiplication by 5, another Boolean variable for division by 4, and a third Boolean variable for adding by 7, means you have 3 Boolean variables which are representing these possibilities. It means you have 8 possible combinations. So if you represent these possible combinations in a truth table, you're able to comprehensively represent all possible combinations without missing anything. And then you could take a starting number and let's say take a starting number of 10 and then do all these operations, and you're able to find all the possible outcomes you can get. So if, let's say, you have the result now and you wanted to go backwards and see what operations were actually carried out on this initial number, you're able to find out. So we're going to represent that particular problem. Then, like I said, you have one example given here, example 1. So you would have to work this out as part of a tutorial. And then you have this third example here, which is as for this here, starting here. Okay, so the next problem formulation is similar to one I have used question is a project. So it's a problem I have used in my master project, which was very effectively solved using this problem formulation analysis using Boolean or variables. So this is something which you would need to also work on. So you have 2 assignments, 2 homework to work on. Let's look at this particular example here with mathematical operations being using Boolean variables to represent whether you are carrying out a particular mathematical operation or not. Okay, so let's I'm just going to share the screen now on the black screen. Let's work this out together. Okay, so I'm just going to bring it down. I hope you can see the black screen here. So as you can see, you have always an initial number, which is going to be, let's say the initial number is X. One minute, so I'm just sharing the screen with you. Yeah. So this is the initial number we are using. Initial number we are using, let's say, is X. It can be any number. Yeah. So if you see the question down, we actually set this value of X. Now we have 3 possible operations. Let's say the first operation will be represented by a Boolean variable A. So A here can be true or false. So A represents whether you multiply, is multiplication by 5 or not. So if A is 0, it means you did not multiply by 5. If A is 1, it means you multiply by 5. So similarly, let's create a second Boolean variable. We call it B, and this is for a division by 4. Okay, so we have a third possible operation. We call it C. So this one is add 7. Okay, so if now we formulate this whole problem as a truth table, so it means since we have 3 variables here, you will have 2 power 3 combinations as we see. So let's construct this truth table here with 8 possible combinations. These are going to be your inputs, and then we have 8 possible combinations. And then so let's put first A, B, and C. Now your output is going to be what? Is going to be simply the result you would get, the outcome you would get when you apply these operations, whether or not, depending on the combination you have. If we start with a value of X, so you can have different values of X. Okay, so let's put in this one here A, and then B, and then C, and this is your outcome. Yeah, your outcome of your operation. So as we have done before, so you're going to just list all the possible combinations. 8 combinations, and then I will say before, this one is going to change every 2 rows, and finally this is going to change every 4 rows. So by formulating the problem in this way using Boolean variables, you're not missing any combination of variables. Okay, any combination between your input variables. So let's say we have a start value of X. You don't multiply by 5. So this is saying you don't multiply by 5, you don't divide by 4, and you don't add 7. Your outcome will be X itself. So you're not doing anything on X. Okay. Now this one is saying, this combination is saying if A is 0 means you did not multiply by 5. So X remains by itself. So you don't multiply by 5 on X. You don't divide by 4. So it remains X itself. And then you add 7. So your result will be X plus 7. Okay. Let's look at this one now. You don't multiply by 5, but you divide by 4 and you don't add 7. So this one's going to be X over 4. Let's look at this one now. So we don't multiply by 5 initially, but we do divide by 4. So now it's X over 4 and then add 7. So this outcome here is going to be X over 4 plus 7. Okay. Let's look at the 5th combination now. This one is saying we simply multiply by 5, but we don't divide by 4 and we don't add 7. So your outcome is going to be 5x. I hope it's clear. So this combination now is saying we multiply by 5, but we don't divide by 4 and then we add 7. So it's 5x plus 7. This combination is saying we actually multiply by 5 and then we divide by 4, but we don't add 7. So the outcome you would get is 5x over 4. Okay. The last one is we're doing all the 3 operations. So we multiply by 5, we divide by 4, and we add 7. So this is 5x over 4 plus 7. Okay, so I hope you've got an idea what this whole topic is about. Formulation. You can represent the different steps that you're carrying out using Boolean variables. So when the value of a given input, Boolean input is 0, means you don't do that operation. When it's 1, you do it. And then you can just list all the possible combinations you can have and calculate the outcome for each one of them. Then you have all possibilities. Yeah, so if we just scroll down and now look at the question itself. So it's saying such a calculation was performed, the starting value of 2. The starting value, assuming it means X is 2 now, and the final answer obtained was 9.5. So the question is saying we actually started with a value of 2. Okay, so X was equal to 2, and outcome you've got was 9.5. So the question asks you what steps did you carry out to obtain this value of 9.5. So what can you do here? You can just replace your X here by, or you could have used 2 directly, but it's good to be those of X. Now you can very quickly just write answer. So if X is 2, so you get 2 here, you get 9 here, 2 over 4, you get 0.5 here. If it is 2, then it is 9.5. No, sorry, it is 2 over 4, so 7.5. If it is, this one is 10. If it is here, so we get 17. Here we get 5 times 2, 10 divided by 4, we get 2.5. And the last one is 5 times 2, 10 divided by 4, you get 2.5 plus 7, so you get 9.5. So in that way, you have got all possible combinations you can have if your starting value was 2. And then since the answer is 9.5 means you have actually carried all the different steps. If, for example, the value was 0.5, you can say now you have just divided by 4 and so on. So this may seem very trivial, but the other example you have later. I'm just going to close this one and then just share the slide again, the handout. So if you look at the second example here, which is now a similar example, but in terms of bits and bytes, which I would invite you to work with. So here it's a bit more complicated, because this is where I've used this method here for packets which are communicated on a LAN, so the Ethernet protocol. You can have some possible operations, Boolean operations on these packets, data packets. And what we find out is we knew the starting packet, and if you are communicating this packet over a local area network, you expect to have the same packet at the end. But for because of electronic circuits, some operations are carried out on this packet. So when you receive your packet, you have to do the reverse operations to determine to get the original packet. So this is where I've used this method for different possible combinations, and then based on analysis, actually a monitoring system which were giving us the input packet and output packet. So I have this information, the input packet in terms of bytes and the output packet again the bytes. So by carrying out this systematic analysis using Boolean variables, by representing each of the possible combinations here which are listed, and then doing the whole series of possible combinations, working out what is the expected output, and then comparing this output to what you're actually getting, I could actually find out what operations are being operated on this particular input packets during the transmission from by the electronic circuit. So this is one quite simple exercise here based on what actually carried out, but representative of this. So I would invite you to work on these two examples. The first one is a person dancing or not, so 3 persons, X, Y, and Z. You go to a party, so is it dance or not, depending on 3 input variables, so temperature, whether it's cool or not, whether the music is oriental or not, and whether it's crowded or not. So try to represent this in terms of a Boolean problem, like we formulated, you can use Boolean variables and then write a truth table. Similarly, try to solve this example here where it's a bit more complicated here, where you have a starting byte and a result, and you want to find out what operations you carried out on the input bytes. Yep, so next topic we take up is Karnaugh map. So a Karnaugh map is a way for you to simplify logical variables. So we've seen earlier, you can use the rules we've seen, like De Morgan's laws. You can use other rules, Boolean rules, to simplify expressions. Karnaugh map is a graphical method where you can actually put your truth table inside this table here. It's like a map, and then you can very quickly simplify the Boolean expressions without doing lots of manipulations like we did earlier. So let's see how a Boolean map is constructed. So you can see the first Boolean map which is constructed here is for a 2-input truth table. So you have a 2-input truth table. We know if you have 2-input truth table, you would have if you have a 2-input truth table, you have 2 power of sorry, let's annotate 1 minute. Okay. So if you have a 2-input truth table, you would have 2 power 2. Do that. So you have 4 possible combinations. So these are the possible combinations which you find here. Okay. So if you have a truth table, let's say for the OR gate, where you have 4 possible combinations, the values taken there. If I just erase this one here, 1 minute. So if you have, if let's say you want to do a Karnaugh map for the OR gate, we know when A is 0 and B is 0, the output is still 0. So you put a 0 here. And when A is 1 and B is 0, you get a 1 here. And when it's 0, 1, you get a 1. And when it's 1 and 1, you get a 1. So this is how the Karnaugh map is going to be for the 2-input OR gate. And then later we'll show you how we can simplify this to get the expression. So in case now, this Karnaugh map, what you find here is for a 3-input Karnaugh map. So since we have 3 inputs, we know we have 2 power 3, so 8 combinations. This is where you have this 4, you have 4 4 columns and 2 rows. It could have also been 4 rows and 2 columns. It depends how you're drawing it. But very interesting here is, since you have 3 inputs, which we are calling in this case A, B, and C. Yep. So you would need to, of course, represent. You could have put A here, B, C, or like shown here, A, B, and then C here. So this, when you put A, B, of course, you have 2 inputs here. This is why it's shown 0, 0, 0, 1, 1, 1, and 1, 0. So the first index that you find here, the first number is corresponding to A, and the second one is corresponding to B. And C, of course, is only one input, so 0, 1. By having these combinations here, you get your 8 combinations. So if you had a truth table with 3 inputs with 8 combinations, you would need to have 8 cells. So this is what a 3 input Karnaugh map would look like. Okay, so very important here is when you look at the input, it's 0, 1, 0, 1, that's clear. But if you look at the way we've written the numbers for AB, so we have 0, 1, 0, 0 starts here, and then 0, 1, but we don't have 1 zeros and 1, 1. If you consider a truth table with 3 inputs, so typically you would have 1, 0 first, and then 1, 1 comes afterwards. But when you're writing the possible combinations for a pair of inputs or for 3 inputs or more, you have to bear in mind that when you change from one here to the next one here, only 1 input can change state. So when you change from here to here, you can see 0. So A is 0, it stays 0, and B is 0, it becomes 1. So only 1 input can change. If you change from 0, 1, and you come down, if you want to put 1, 0, can you see now your A has changed to 1, and your B has also changed to 0. So this is not allowed. So this is why you have to first go through 1, 1. So if you go through 1, 1, you can see now your B is remaining 1, but it's now your A change. Only 1 input can change at a time. And when you go now from 1, 1 to 1, 0, now A is not changing because it's remaining 1, and B changing. So this is why we have this. You have to pay attention. If you don't do this, your analysis will be wrong and you won't get the correct expression. Make sure you bear that in mind when you're drawing your Karnaugh map. Okay, now let's see how do we actually apply the Karnaugh map to simplify logical expressions. Okay, so we've seen how to construct a Karnaugh map, and let's take some examples now. So if you wanted to construct a Karnaugh map for, let's say, logical gate and logical gate, so the truth table is shown on the left here. We've come across this before. So this is how you construct your Karnaugh map. It's 2 inputs. We have 4 cells, and you can say A is 0, 1, and then B 0, 1. And then if you look at the truth table, when A is 0, B is 0, so the result is a 0. So this 0 is at 0 here. When your A is 1 and B 0, so A is 1, B is 0, so you get a 0 again. When A is 0 and B is 1, so A 0, B 1, you get a 0, so you just put it here. And finally, when both inputs are 1, so A is 1, B is 1, you get a 1. Yep. So in this case here, when you are dealing with Karnaugh map, you're going to, next step, you start looping the ones. So in this case, it's just 1, 1. So you just have 1 loop and then that's it. Yep. So later, the next example we'll consider for or we'll have loops where you have more than 1, 1, then you have to loop the ones together. So in this case, it's a very simple, trivial example. When you get this, so when you get this combination here, so this one only, so this expression here, if you want to write it, so if this is the output is Q, is equal to, so this is a single loop. So in a Karnaugh map, you always loop the ones. You don't consider zeros. That's an important observation that you need to bear in mind when you're dealing with a Karnaugh map. You always loop the ones, not the zeros. In this case, just 1, so just loop it, and you can see where this one is occurring. A is high and B is high. So it's A is high and is a dot, B is high. So this is a Boolean expression you get, which we expect because this is the AND gate. This one is pretty straightforward. The answer is Q is equal to AB. Yep. So because of only 1, 1. But let's see now if we get other examples. Let's see how it works out. This is how you're going to operate when you deal with Karnaugh map. Now the next example you have now is the OR gate. Let's see how the OR gate works in a Karnaugh map. So as we've done above, so if you have a 2-input truth table, you will have 2 inputs here. Yep. So you have 4 possible combinations. So your A01, B01, that's straightforward. Now just look at your truth table. Now when A is 0 and B is 0, you have a 0. So this is 0 here. And then when A is 1, B is 0. So A is 1, B is 0, you have a 1. So this is a 1 here. When A is 0, B1, so A is 0, B1, you get another 1. That's a 1 here. And when your A and B are both 1, is a 1. That's a 1 here. Now once you've done that, you will start looping. Yep, you will start looping the ones. So you have to start looping the maximum number of ones you can have in steps of 1, 2, 4, 8, 16, and so on. So you will never, for example, loop 3 ones together. You will never loop 5 ones together, or 6 ones together, or 7 ones together. It has to be either 1, like we had for the end. There's no other possibility. This is the lowest number of ones you can have, but you would want to start big first. So in case you have a Karnaugh map with 4 cells, the maximum you could have loop was 4, but in this case, we can't loop 4 ones, there are only 3. So the next maximum number of ones you can loop would be 2. So this is what we've done here. So when you loop, you can loop vertical, horizontal, not diagonally, but you can also loop circular. Means if you have a 1 here, you could loop this one with this one as well, that also works. Or you could loop this one with this one, especially in larger Karnaugh maps, which we'll come across later. So the obvious looping which you're going to perform is as shown here. So you just loop these 2 here. So this is a vertical looping with 2 ones, and then horizontal looping with 2 ones. Once you've done that, all the ones are looped. You don't create further loops, because every loop is going to create a Boolean expression. And if you write unnecessary, if you loop more number of ones unnecessarily, you have more expressions, then you have to simplify later. So once you have looped all the ones, in this case, the maximum number of ones we could have looped is 2, but there are no more ones left. So we don't need to loop any one individually like we did here for the end. Yeah, so in this case, we have looped all the ones together using 2. So now the next step is to write expressions for these loops. So I'm just going to use a different color for the 2 loops so that you can get the expressions clear. Okay, so let's loop this one in blue. So this is a second loop, which we now need to write an expression for. So let's write the expression for the red one first. So once you've looped, you have to write an expression. So if you look at this loop here, what do you find? Actually, your A has not changed. Yeah, your A has not changed. Your A was 1 here. Since it's vertical, A was 1, it stayed 1 here. Whereas your B has changed from 0 to 1. So anything which changes actually is eliminated in the expression. So since B has changed from 0 to 1, it will not appear in the expression for this loop. So A has remained 1, so it's remain high, it's going to be high. So this is going to be the expression for this loop here. Let's look at the blue loop now. Let's write an expression for this blue loop here. So if we look at the expression for what changes we had in the input, so when you look at this loop here and going from this one to this one, you find A has changed state, so it will not appear in the expression for this loop. On the other hand, B remain high, so B remain high. Okay, so if you want to write now expression for the whole for Q, yep. So you can write now Q is equal to, so it's now A, which is for this loop, plus B. Because why this plus here? Because an O here. So it's either this one or this loop. So the expressions you get for the different loops in a Karnaugh map are going to be always all together. Yeah. So let's look for some further examples. So we've seen the creation of Karnaugh maps for the end and then the O. So the answer we've got is Q is equal to A plus B, which is the expected logical expression you get for the O function. Yep, we know that right from the start. See what we've written earlier when we were actually writing a mathematical expression for the O function. So some explanations are given here, so you can read on them. Let's now consider this Karnaugh map for a free input NOR gate. So if you look at the truth table here, the free input NOR gate would be addition of everything and then inverting, yeah, because the NOR gate is not O. So if you add all this, so wherever you have a 1, the output will be 1, the inverted becomes 0. So it's a very straightforward truth table. So you can see the 7 here would be all zeros because you have at least one somewhere. Whereas the first row here, you have all zeros. So when you 0 plus 0 plus 0, you get a 0, and then you invert it, becomes a 1. So you can see how the Karnaugh map is constructed now for a free input truth table. So like you see earlier, you have AB is 0, 0, 0, 1, then 1, 1. Be very careful here. Then 1, 0, and then C is 0, 1. So only one combination is 1, where all the free inputs are 0. So you get your 1 here, and the remaining are 0s. So in this case, the simplest looping you can have is just this one. And the if you want to write now a logical expression for this loop here, so I'm just going to annotate. Yep, if you want to write a logical expression for this particular loop, this is simple here, just one. So you can find everything is low here. So it's a low, A is low, and B is low, and C is low. Now, if you apply De Morgan's law, we know actually this is going to be A plus B plus C complement. So this actually is what actually the no operation is. A no operation is not O. So O would have been A plus B plus C, and then you complement because of no. So you can see here, but be careful when you use a Karnaugh map, you always get ends. Yep, you always get ends. And then why you have complement here? Because A is low, B is low, so they are complemented, and C also is low for this combination. Again, we don't consider the zeros when we write expressions for the Karnaugh map. You can see now by simply formulating the problem this way, we can get the result very quickly without any further manipulation. We get the result directly. Yeah, but if you want it, of course, in this form, which is more familiar for the operation, you can just apply De Morgan's law once and you get it back. Okay. Let's move ahead and consider some more cases of Karnaugh maps. So this is an arbitrary truth table. So it's just a truth table which at start we don't know what operation this is. So you can get problems like this. For example, in the example we had above on the person dancing or not. So you could first write a truth table and then do the analysis to find logical expressions for persons X, Y, and Z by formulating Karnaugh maps for each one of them and get an expression for X, Y, and Z in terms of your logical input variables. So let's consider this example here where we don't know at this point what logical expression this is. It doesn't need to be N or XO, XO, XO every time. It could be a new logical expression which is a combination of these ones. Okay, let's look at the truth table first. There's two inputs, so you can see you have 4 cells in the Karnaugh map, and then you start populating the Karnaugh map. So when A is 0, B 0, this is the 1 you find here. When A is 1, B 0, so A1, B 0, so you get a 1, that's a 1 here. You find that now when A is 0, so A0, B1, you get a 0 here, and then when both are 1, when both are high, we get a 1 here. So this is what you get. So the first loop you're going to generate, like I said, it has to be horizontal or vertical. In that case, you have maximum 4 cells. The maximum number of ones you could have grouped is actually 4. But since you have a 0 here, you can't group 4 ones. So you can now group 2 ones, as we can see here. So the first loop we can create is a horizontal loop here. So we can group this one with this one. That's the first loop you're creating. And the second loop you're creating is as follows here. So we can group these 2 ones together. So you will notice that this one is used 2 times. That's not a problem. As long as you can group a maximum number of ones together to attach a given one to a loop, you can do that. But once you group all the ones, there's no point now in trying to group the ones further. That's what I mean. Okay. So you created your 2 loops. Now let's write expressions for each loop. Okay, so for this red loop here, if you want to write an expression for it, so again, like we done earlier, so as you go across this horizontal loop here, you can say A is actually changing from 0 to 1, so it will not appear in the logical expression, whereas B is remaining low. So this loop is going to be not B, because B is low across this loop. It's 0, so it's going to be not B. Now, if you look at the blue loop, this loop here, so if we analyze the variation of A and B, so B actually changes from 0 to 1. You can see here, so B will not appear in the expression, whereas A remains high. So A remains high. So if you write now an overall expression for a Q, so it's going to be Q is equal to A or not B. So this is the logical expression you would get for this particular truth table. So you can see here it's not actually, it's an O here, but it's not A or B, it's A or not B. So using the Karnaugh map, we could very easily and quickly get the logical expression for this truth table. Okay. Let's move ahead. So you have other examples here, which I would invite you to look at now. So this one is an arbitrary truth table for free inputs. So I would invite you to look at that and write the expressions. So it's clearly explained here the various possible combinations, but just bear in mind you would never loop 3 ones together. So you would loop maximum 2 ones. Actually, the handout here would actually show you that there's no point in looping 3 ones. You would actually going to loop 2 ones maximum. If you could loop 4 ones, that's fine, but in this case, you are not able to loop. So it's out of 1, 2, 4, 8, 16, depending on the number of ones you have. So you have some examples given as well for you to try, and you will have it in your tutorial sheet as well. The next topic we look at related to Karnaugh map is something called maxterm and minterms. Okay, so another way you can write expressions, Boolean expressions from a truth table using the minterm concept. So what is a minterm? A minterm is a product of terms. Okay, so if you look at the particular truth table here, okay, so if you look at this particular truth table here, where you have, let's say, annotate. Yep. So if you look at this truth table here, so you can see your all inputs are low. So the minterm which you have is not A, not B, and not C. Yep. So the minterm is a product of terms. Be careful. Just bear that in mind. Your minterms are a product of terms. Maxterm will be sum of terms. So we look at the maxterm in a few minutes. So the minterm is, if A is low, this is why it's complemented, but you take the product of all of them. So if you look at this particular combination here, where your A is high, when your A is high, so there's no complement for the A, and then B and C are all both low, so they are complemented, and then you're always ending the various terms. So in the similar way here, you can see we have all the minterms listed. Yeah. So since this is 0, 0, 0, we call this one minterm 0, minterm 1, 2, 3, 4, up to 7. Yeah, because you have 0 to 7, because you have 8 combinations. Yeah. So once you're able to write your minterms, how can we use them? So let's consider the AND operation, and I will illustrate that. Then you can apply the same for our truth table. So if you consider the AND truth table here, so you can write minterms for all these combinations. So this is not A, not B. This is A, not B. This one is going to be not AB, and this one is going to be AB. So this particular combination here, this one is going to be A is high. Sorry, just do that again. Erase. Yeah, so this is A is high and B is high. Now, important observation again is when you consider minterms, you take the output where it is high. Yep. So in this case here, the only combination where you find your output is high is here. So you just need to write the expression as Q is equal to A and B. So this is a minterm, only one minterm. So your expression would have only one minterm. It's done. And you expect this to be of this form because this is your AND operation. Now, what about XNOR, for example? So let's look at this truth table here. So if you wanted to write minterms for this one as well, so you look for all places where your all the combinations where your output is high. So these two. So then you write the minterm for this one. So what is going to be the minterm for this one? So it's going to be A is low and B is low. Okay, and this combination is going to be A is high and B is high. So the final expression is going to be as follows. You take now the product of terms, and then when you merge them together, so Q is high for this combination, fine, or for this combination, because you have two possibilities. So when we say or, we have to add. Yep. So this is how you can write minterms for all the rows in your truth table where your output is high, and then you just all these possible minterms or minterms of product times. Okay. Let's look at some other examples. So you can just read through the notes, but that's basically how it is used. Now next is a max term. So max term now would be a sum of terms. So instead of, so if a max term is not going to be the product of terms, it's going to be sum of terms. So if you look at this truth table here, which is for the operation, yeah, is for the operation. So the max terms will be as follows. So you expect, if you wanted to write this one, maybe logically by intuition, you would say this max term here is going to be not A, because like I said, max terms on addition, you're going to add low like this, and this one is going to be not A or B, and this one is going to be sorry, a small mistake here. So this one is actually for this one here. So for this one here, it's going to be A or not B, and the final one, maybe by intuition, you will say is A or B. But that's not how we write it actually. When we talk about max term, we consider only the rows where your output is low. So it's a contrary of minterm. For minterm, remember, we considered only the rows of your truth table where your output is high. So for max term, we consider only the rows where your output is low. So that's one first very important observation. And when you write the max term, that's fine. We take the O of your combinations. But important is, for example, the max term for this row here is actually going to be A plus B. So when A is actually low, we do not complement. So in this case, A is low. We would expect it to be complemented, but since this max term corresponds to the output where you for combinations where your output are low, for the combinations where your output state is low, so we actually don't complement when it's low. It's opposite. We're taking everything opposite. So we are O-ring, that's fine. This is our max term. But when A is low, we don't complement. When B is low, we don't complement. So if you wanted to write a max term for this one now, based on what we've said, so now you can find your A is actually high, so you would complement it, and then plus B, which is low, it's not going to be complemented. If you write the max term for this particular combination, this particular row here, you find your A now is actually low, so it's going to be high, you don't complement, and your B is high, so you would complement. And this max term here is going to be complemented for both, because both are high. Okay, but when you write your term now for your logical expression for Q, like I've just said, I'm just going to clear all this. So when you want to write Q now, you would consider only the row where Q is low. For max term, we consider low. So your output would simply, in this case, be Q is equal to A or A plus B, which you expect because this is, again, the O function. So important difference between minterm and max term. If I just summarize, minterm, you take product of terms, first thing, so you don't add the product of terms for a particular row, and you consider those combinations, those rows in the truth table where your output is high. Whereas max term, you will take the O-ring of a particular, for a particular row, you will actually add all the various states, the various input Boolean inputs. That's the first thing. So you're going to add them, and here you will consider rows in your truth table where it is actually low, and the way you write your max term is totally the opposite of what you use for minterm. So if your particular input is low, you actually do not complement, and where it's actually high, you would complement. Okay. There is a similar way here. We can write. So we can write a truth table like this. Just clear drawings. Okay. So you can simply write the truth table to give max term numbers if you want. Okay. So again, like I've said, if you consider this combination C, B, D here, you can find all are actually low. So you can find it's written A, B, C, because when it's low, we do not complement. In this case, your A is high, we complement A, but B and C are low, so we don't complement, and it's all added together. That's important to understand. Now, when to use minterm, when to use max term. So it's a summary here of minterm, max term. So it's a nice place. So when do we actually use minterm or max term? That's the question. So let's say you have a truth table like this, and you want to actually write an expression for Q. Yep. So if you want to write your minterms, you would consider these combinations here, where your in your output Q are all high. Yep. So if you wanted to write Q in terms of minterms, you're going to consider these ones. If you want to write your Q in terms of max terms, yep. So I'm going to just highlight them in blue now. So you would consider these ones. You will get exactly the same answer if you use minterm or max term. Yeah, depending. So you would choose typically one. This question is asking to do for both. Yep. So you can also use a Karnaugh map to analyze a problem. So I'm just going to guide you for one of them, and then you can do the rest. So let's just try to write the minterm. Yep. So in this case, you find a 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 minterms. Yep. And you have 3 max terms. So if you want to choose between, if you had the discretion to choose a particular approach to solve this problem, you would most likely go for max term because there are only 3 terms here. Yep. So the max term that you will write for this one here in blue color. Yep. So the max term. So based on what we've discussed earlier, so what is going to be this max term here? Yep. So this max term, you can say x is actually low. So for max term, we don't complement the low, and it's always added. Y is also low, so we don't complement y. And then you find the z is actually high, so you would complement the z. Yep. Now, what is the max term for this one here? So you would x is low, so you don't complement. Yep. So you find your y is actually high now, so you would complement y, and then your z is low, so you will not complement z. Finally, this particular max term there, you find your x is high, so you complement. Your y is low, so you don't complement, and your z is high, so you complement. So how you write Q now? So Q is going to be the product of these 3 max term. Yep. So we take product of max term, okay, and we take the addition of minterms. Okay, so this is how you can write the expression for Q in terms of your max term. In case you wanted to go for minterms, then we're going to consider this one. So what is going to be this minterm? So minterm where it is low, you actually complement. So this minterm is going to be x like this, z. So this is going to be this minterm. This one, the minterm is going to be x bar and y and z. Okay, so this minterm here is going to be x is high, so we don't complement, whereas y is low and z is low, so you complement. For this minterm here, your x is high, your y is high, but your z is low. And finally, here for the last minterm, you can find all the inputs are high, so these are you don't complement anything. And finally, if you want to write Q now in terms of minterms, you would just add all this together and you get the expression. Yeah, but the answer you get is not necessarily in a simplified form. Then you would need to start applying rules to minimize it. So this is where the Karnaugh map is very useful, because from the Karnaugh map, you directly get the minimized expression. It's a question of what approach you want to use. So you could do that now. You can write your expression and then try to simplify using the rules we've seen above. And you can also use a Karnaugh map to get a simplified expression for Q using the Karnaugh map. Okay, so this completes this section here on maxterm, minterm, Karnaugh map, and also a program formulation using Boolean variables. Now, this section here on half adder and full adder is not, it's just given here in your handout for self-reading. It's not, you won't be assessed on that. So it's an application of logic gates where you can do addition using logical gates. Yeah. So this is just for self-reading as an application of Boolean algebra and logic gates. Yeah. So for your syllabus, you're stopping here at maxterm minterm for this section. So I end this video here. Thank you very much for your attention. So I'll be sending out the next tutorial sheet to you based on this. Thank you.